first time in history a spacecraft had the courage to enter the Sun's atmosphere. This achievement of the Parker Solar Probe will always be remembered in history, because no metal or the hardest rock in the world can withstand such intense heat. The question then arises, why doesn't the Parker Solar Probe melt in such extreme temperatures? Not just in the hundreds, but tens of thousands of degrees. In the early 1900s, scientists discovered an unknown phenomenon during their research on the Sun. They were studying the wavelength and color of light from the Sun to estimate its heat. This task was performed from Earth with the help of a spectrograph. It is essential to note that the color and wavelength of light are directly connected to its temperature. The results seen by scientists created a mystery that remains incomprehensible even today. They observed that the Sun's surface temperature is 5,500 degrees Celsius, but its outer atmospheric layer, the corona, has a temperature of more than 500 degrees Celsius, which is 100 times hotter than the Sun's surface. This is similar to feeling hotter when moving away from a fire. This unusual phenomenon has puzzled scientists for almost a century. Normally, this layer is hidden due to the Sun's light, and it is only visible during a solar eclipse or by using a chronograph sunshade. In 1958, after the establishment of NASA, many space missions were initiated, one after another. Satellites and spacecraft ventured into space. But to understand this unusual phenomenon of the Sun, it was necessary to create a space probe that could enter the corona layer and study what was happening there. This probe would have to endure 500,000 degrees of heat from the Sun's rays. However, this task was not easy, and it was almost impossible to imagine, as even iron has a melting point of 1500 degrees, and the world's strongest metal, tungsten, melts at a temperature of 3,422 degrees Celsius. This means that the surface of the Sun can melt any material within milliseconds. Considering this, one can only wonder what the probe would face upon entering the corona layer. The designing and development of the Parker Solar Probe posed a challenge, but reaching it near the Sun was an even bigger problem. It is important to remember that any satellite leaving Earth's orbit needs to re-enter the Earth's orbit, reducing its speed, so that Earth's gravity can affect and attract it. Similarly, to send a satellite to another planet, its speed is increased to escape Earth's orbit. Suppose we want to send a spacecraft to Mars first with the help of rockets. It reaches Earth's orbit, and then with precise timing, speed, and angle, it escapes Earth's orbit. Getting out of Earth's orbit is an energy-consuming task that requires rockets. However, once outside of Earth's orbit, there are no rockets available. So small rockets are used on the spacecraft to gradually increase its speed and escape the orbit. Because Mars is relatively close to Earth compared to the Sun, the angle at which the spacecraft is launched is not very significant. But since the distance between Earth and the Sun is 150 million kilometers, getting out of Earth's orbit and entering the Sun's orbit requires a larger angle and a considerable amount of energy. Such an immense amount of energy has not yet been created by any rocket. Thus, NASA's experts decided that before heading directly to the Sun, the Parker Solar Probe would be sent to Venus first. By using the gravity of Venus, the Parker probe speed could be increased. However, there was a problem, because Venus is a smaller planet with low gravity. To achieve the required speed for the Parker Solar Probe to reach the Sun, it had to circle around Venus 24 times. To get close enough to the Sun, on August 12, 2018, the Parker Solar Probe was launched from Cape Canaveral Air Force Station, and NASA planned an 8-year mission to reach the closest point to the Sun. The Parker Probe would make use of Venus's gravity 24 times, with each orbit having 37 hours, allowing for solar research to take place. In total, this probe would conduct 900 hours of research on the Sun over the course of 8 years. On April 28, 2021, NASA confirmed that the Parker Solar Probe successfully completed its 8th orbit in the Sun's corona layer. The mysterious phenomenon of the corona layer being 100 times hotter than the Sun's surface was confirmed by the Parker Solar Probe. However, the research continues to determine the reasons behind this, and what powers the corona layer to be so much hotter than the Sun's surface. Now let's address the main question. Why doesn't the Parker Solar Probe melt in such high heat? The side of the Parker Probe facing The sun has a heat shield made of carbon foam, specifically designed to absorb the sun's heat. This foam is 97% empty from inside, making the heat shield more effective. Additionally, a carbon-carbon composite layer is coated on both sides of the heat shield, created from graphite and resin. The mixture is superheated, turning it into the purest form of carbon. Carbon has excellent heat conductivity, and on the side facing the sun, the heat shield is also coated with white ceramic paint reflecting most of the sun's light before it enters. Furthermore, the Parker Solar Probe is designed to stay behind the heat shield at all times. Despite all of these measures, the Parker Solar Probe can handle temperatures up to 2,500 degrees Celsius, while the corona's temperature is 500,000 degrees Celsius. The explanation of how the Parker Solar Probe handles such extreme heat is relatively straightforward. According to the law of thermodynamics, heat is transferred through a medium. For example, in summer, particles in the air and water vapor carry heat, making us feel warm even at night. When there are fewer particles, heat transfer is more challenging. For instance, placing a hand in boiling water can cause a burn quickly. But in a 300-degree oven, the hand can be quickly moved in and out without feeling the heat. This is because water molecules directly touch us, whereas in an oven, nothing touches us. Experts state that if the Parker Solar Probe's heat shield reaches temperatures of 1,200 degrees Celsius, the back part of the probe where sunlight doesn't reach experiences freezing temperatures, because there are no particles to transfer the heat. This is why the Parker Solar Probe does not melt even after going so close to the sun. I hope you like and share this NOR TV video. And also subscribe the channel for more interesting videos.